Hi guys, alright, let's get this whole thing going here and get back into it. So, bonding basics and then ionic bonding. I'm going to try to go through this faster than my normal clip, so here we try. Okay, chemical bonds. Force that holds groups of atoms together and makes them function as a unit. So that should be pretty straightforward. So a lot of this beginning stuff should be straight from honors and regular and should be things that you guys already know. Those bonds are going to control all the physical properties and a lot of the chemical properties of a substance. Um, so, melting point, hardness, electrical and thermal conductivity, solubility, just as some examples. Um, so the big question then is why would something bond? So we've talked about bonds all the time, and we talked about like which ones are more thermodynamically favorable and all these other things. But the like bare bones, why do they bond together? Well, this is probably the best way to visualize why they bond the way they bond. Um, so up here, if you have two, we'll pretend these are both hydrogen atoms. So you have two hydrogen atoms and they are too close to each other. If you push them too far into each other, there's a lot of repulsion that happens. The electrons are repelling each other, the protons are repelling each other, and so they basically force their way apart. So the potential energy here, you can see it's way up here on the graph. These push away from each other. It's like trying to push two north poles off a magnet towards each other. The closer you get, the more resistance there is. As you come down here, you get to a point where there's some overlap and some attraction. So this is where bonds actually happen. So you want them the appropriate distance where there's more attraction than there is any repulsion forces. And then if they get too far apart, well, then there's no attraction at all. So this is like the key place when we're actually talking about things that are bonding. Um, Perfect amount of distance, perfect amount of attraction, lowest potential energy point. Um, and if you notice, there's even lower potential energy than when they're just not anywhere near each other at all. So this is why bonds form. Um, they have the lowest, this is the lowest potential energy state that they can be in compared to being separate from each other. Okay, so like I just said, they bond to achieve lowest possible energy. The most chemical substances are compounds, not elements. So generally, we see that out there, elements like to be in bonds and in compounds that generally don't float around by themselves. Um, Being bound requires less energy. It takes less energy. It takes energy to break that bond. Like you actually have to put energy in, and then when you do break it, there's that release of energy. Um, so you break them, and then there's a release of energy when they form because it's that lowest potential energy state. Okay, zooming in so you guys can see this one. This throws back to a little thermo. So bond energy, the energy required to break bonds. So back in thermo, we talked about this as a math problem. Um, two hydrogen atom or two hydrogen molecules here plus one oxygen here to make water. Well, you have to put energy in to break these bonds and these bonds, and there's the amount of energy required, 436 here for each of these, 498 for this double bond, and then you form all of these bonds. Well, there's this energy release that happens when you do that. So energy required to break is this, energy released when you form them. You can graphically look at that. So here's the activation energy, here's the energy released, and since this extra amount of energy exists, there's this negative 486 kilojoules. This thing is exothermic from that bond forming. Okay, so types of bonds. There's ionic, covalent, and metallic. So we talked about both of these in honors. So this is basically a review. Metallic should be pretty new, and we honestly still don't really talk about this very much in AP, but you'll start to see a little bit of it. Ionic bonds happen as an electrostatic attraction. So zooming back in here, um, you have sodium that gets an electron to chlorine. When that happens, This guy becomes positive, this guy's negative. There's an attraction because of the electrostatics, because of positive and negative. Opposites attract. So, transfer of electron, usually involving metals and nonmetals. Those can include polyatomic ions. Strong attractive force between positive and negative. They usually have a simple, like empirical ratio that they're expressed by because they form these large crystal solids. So anytime you look at table salt, this is what you're looking at. So the simplest unit for that is 1 sodium and 1 chlorine, but this is the overall. Generally have high melting points because of those strong electrostatic attractions. And they, again, like to make these crystalline structures that just depend on their ratio. Covalent bonding occurs when electrons are shared, so there's not that transfer anymore. So they're sharing electrons so that they can fill up their outer shells. Usually involve two nonmetals. Basically, metals don't do this kind of thing. Attraction between nonmetal atoms. You can form large structures, complex structures this way that are more than just crystalline structures. And then they're given a true ratio, so a molecular formula. So that's why ionic compounds and molecules are different. Usually lower melting points, but that's not always true. And then maybe in any form at room temperature, so solid, liquid, gas, etc. So looking up here, methane is a gas, ammonia is generally a liquid, but has a fairly low boiling point, and then water generally is a liquid. All right. So melting or metallic bonding, this is the new one. So metallic bonding is basically a sea of electrons. So you can kind of see that down here. So you have all of these zinc atoms that are right here, and you have these electrons that are literally just floating freely between them. Sodium does the same thing over here. So metals, when they bond together or group together with similar metals, they kind of just are constantly passing electrons around in a very random manner. If you organize the way that they do that, well, that's basically what electric current is. So there's all these electrons that are kind of just free floating between all these zincs. They're becoming positive for a second and then becoming neutral and then becoming slightly negative for a second. And so there's just kind of this free flow of electrons. Attraction between metals, ions, and electrons. So you have all these attractions that just pop in and out because these things become positive or whatever for a second. A range of melting points because it depends on valence electrons and attractions and a bunch of other things. So some metals have a really low melting point. Gallium is an example of that. It melts basically in the palm of your hand. And then you have things that are like iron that melt at like 1500 degrees. So usually they're crystalline-like. They're not the exact same as ionic crystalline structures, but similar base idea. Okay, electronegativity. So the ability of an atom in a molecule to attract shared electrons to itself. So basically, how good is it at tug of war? So there's a Linus-Pauling scale to this whole thing. Fluorine is the most electronegative. Francine is the least electronegative. Noble gases, at least the first three, generally don't ever get involved in compounds, so they don't really have values at all. So generally we don't really, that's why fluorine is the max of this and not helium, because fluorine is the only one of the two that actually gets into a compound in any way. So this goes back to our periodic trends a little bit. So fluorines are highest, francium is our lowest, and then these guys don't participate. And these guys don't exist long enough to really have values. Okay, so atomic structure. Why is fluorine the most, and why is francium the least? So a little bit of review. This is something we saw in the summative as well, and for the most part, people were kind of on the ball, but we'll try to get that information back to you guys. So fluorine has the highest Zeph. It has the highest value effective nuclear charge based off of its effective nuclear charge. So when you subtract the core electrons from the protons, you get a Zeph of +7. And it's the smallest +7 that exists on the periodic table. So that's why the nucleus is closest to the action. So it has the highest Zeph that can get the closest to whatever else it's trying to attract. Francium is the exact opposite, so it's only a +1, because if you subtract all of its core electrons, there's only one proton left. So it also is the largest. It goes to period 7. So, it has 7 different energy levels to it, whereas this guy only has 2 energy levels. This guy has a Zeph of 1. This guy has a Zeph of 7. So 2 factors that play into this. Effective nuclear charge and its size for both of them. All right, so difference in electronegativity determining the type of bond that forms. Well, if it's a tug of war, basically, if the two things that are in that tug of war are pretty even, you're going to end up with covalent compounds. So if oxygen is tug of warring against oxygen, that's 0 electronegativity difference. They're both pulling the same strength. You would really struggle to beat yourself in a tug of war because you're literally fighting someone with the exact same characteristics as you. As those values become larger, as that difference between the two atoms gets larger, you end up becoming moving from covalent to polar covalent. So they're sharing, but not quite as evenly. Fluorine does this a whole lot because it has such a high electronegativity. And then you get to a point where the strength difference is just like on a completely different scale. And now you're no longer losing a tug of war battle, you're just straight up getting something stolen from you. And so that's where Ionic comes in. The electronegativity difference is so large that there's a straight transfer of electrons. They're not tug of warring anymore. Someone is just straight ripping the entire rope out of someone else's hands. So this is kind of the ballpark range for everything. There's definitely special cases where things fall into this category but still act covalent. There's things that fall, slightly into the polar covalent region that act ionic. It's a little strange, but this is the general breakdown of everything. Nonpolar is usually considered 0.4 or below. Polar covalent is anything above nonpolar, but still less than about 1.7-ish. And then ionic is generally anything greater than 1.7 difference. Okay, so practice. Determine what type of bond will form and rank the following bonds in order of increasing polarity. So you guys should probably pause it, try this out, but I'm going to go ahead and pause it myself. I'll throw up the answers and then we'll go from there. And there's all the electronegativity difference values. So if we're doing this in increasing polarity, so from lowest to smallest, this guy's number 1, and then we have number 2 right here. Number 3 is this guy. Number 4 is our oxygen hydrogen, and then number 5 is fluorine to hydrogen, which makes sense because he has the highest electronegativity. So this is the lowest polarity, second, third, fourth, and then highest polarity right here is number 5. And so you can see all that in terms of work and answers, and here's it written out in order. So electronegativity and bond polarity. So electronegativity determines polarity since it's measured based off of the nucleus pulling on bonded electron pairs. So the electronegativity, of course, generally ranges from 0 to 4. So this is fluorine. This is really nothing, is 0, but um, francium is going to be the closest to 0.7, I think. So when two nuclei are the same, it's nonpolar, they're sharing. If one is noticeably stronger than the other, then you get polar, and then when electrons are just straight up stolen, that's ionic. And that brings us to ionic bonds. I'm going to change the view here really quick. So valence electrons in each group. So the alkali metals have one valence electron, alkali are 2, 3, 4, 5, 6, 7, and 8, with the exception of helium up here. So ionic charge is going to be represented based off of how many electrons are stolen. So we saw in the last unit that there was a whole ionization energy chart thing where, hey, first ionization energy for these things is really low, but second ionization gets higher because you're stealing core electrons at that point. Well, that's why the charges all match up with those valence numbers. So the things that are set up here, these column 1 guys like to make +1 charges because their first ionization energy is low. Their first and second ionization energies are low in the second column. There's a lot of weird stuff that happens with the transition metals. So there's a few kind of guarantees that you can see right here. And then the non-metals tend to take electrons, so they're picking up electrons that become negative. So -3s, -2s, -1s, and then they don't really bother at all. So name the following ionic compounds or write the formula. So I'm going to, again, say you should probably pause it and do this. It's just quick review from honors. And there you have it. So there's at least the compounds for the first 3. So potassium oxide is K2O, iron 2 oxide is FeO, iron 3 is Fe2O3 because of the charge difference. And then I would write out these names, but honestly, writing is difficult in my current setup. So I'll just say them. This is potassium sulfide. This is potassium sulfate. And then this is copper 2 nitrate because you need to include his charge since he's a type 2 metal. This graph shows energy changes involved in forming lithium fluoride. So from the elements, from the pure elements to the compound itself. So enthalpies of dissociation. So back to that thermodynamics a little bit. So basically, we have this net overall change. Lithium solid becomes lithium gas. Fluorine gas needs to break up to make fluorine gas that's not F2. Lithium here needs to lose an electron. Fluorine needs to gain that electron, and then they need to attract each other. So we are going and pretty much following this path right here, up, up, up. So all the activation energy required, and then all the formation stuff that happens to get to this point. So basically, the overall drive is we're getting from here to here, but we have to go through all this energy change to do that. So activate this, activate this, activate this, transfer the electron, and then finally the attraction and its lowest energy potential point. All right, so Coulomb's law. It's used to calculate the energy of an ionic bond. So we have E here's energy is equal to this constant, so 2.31 times 10 to the -19th joules times nanometers, so that's the distance factor. And then we have the charges involved here. So that's the numerical ion charges, whether it's a +1 or a +2 or whatever, divided by the radius. And because that distance really matters, that's in nanometers, and this is probably the most like, this will have the largest effect on this equation. So negative signs on energy if Q1 and Q2 have opposite signs. So going back here, if Q1 is positive and Q2 is negative, this thing should be negative because there should be an attraction. So there should be energy involved in that, and so there should be a negative value here. So it should be exothermic, and then attractive forces so that the ion pairs have a lower energy than the separated ions. Basically says these ions want to be close to each other, they want to attract each other, so they're going to release energy when they hit that lower potential point. You can also use Coulomb's law to calculate the repulsion forces. So if you had two protons, you could calculate how much they're trying to repel each other, and you should get a positive value there because they're trying to repel each other, trying to push each other away. So lattice energy, notice this is very, very similar to Coulomb's law. So K is now proportional constant here, so they replace that constant in coulombs with K. Hey, look, another K for you. So lattice energy is equal to K times Q1 times Q2 over R. And the solid, so it's K here depends on the solid and the electron configuration of the ions. So energy of attraction depends directly on the magnitude of the charges. Higher the charge, the greater the attractive energy. And then inversely on the distance between them, so greater the distance, the smaller the attractive energy. And this factor probably plays a lot into things based off of like ionic structure and based off of size of quantum numbers and everything. All right, and then home stretch. So there's a little practice here. Which compounds in each of the following pairs of ionic substances have the most electrothermic lattice energies, and justify your answer. So you should pause and try to answer this yourself and see if you can do it, because this is new information for you guys, but I will throw up the answer here in just a second. So 3, 2, 1, and there's your answers. So Na is going to have, NaCl has a larger lattice energy than KCl. Now, if we look at this, this is a +1 and a -1, and so is this and this. So going back here, the only difference, the only factors that play into it is charge and distance. Well, the difference here, they have the same charges, +1, -1, +1, -1, but NaCl, or sorry, Na, sodium here, is smaller than potassium. So because this guy is smaller than potassium, that means he's closer to chlorine. That means that there's this +1 is closer to this -1. So there's a higher lattice energy here. So this is simply because of the distance that this guy has compared to to potassium. And that's just because this guy is a group 3, period 3, this guy is in period 4. So there's quantum number 3 here, quantum number 4 here. So smaller total element. Here, now we do have a difference in charges. So we have magnesium, which is a +2 in both cases. The hydroxide here is only a -1. It takes 2 hydroxides to balance this thing out. Whereas here we are talking about a +2 and a -2. So if we go back, the charges respectively become +2 and -1 for the first guy versus +2 and -2 for magnesium oxide. So this guy has a higher Q value, so Q2 is larger, so that means that this overall lattice energy is stronger. So there's that. Quick little review of atomic theory for everything. So ionic radius is determined from the measured distance between the center of the two things. So cations are one or more electrons have been removed. So these things are smaller than their parent atoms because they've shrunk into their core electrons. Anions have gained an electron, and they are larger because that electron gained is repelling all the other electrons in that same energy level. They're pushing you away from each other, which slightly increases that energy level. Isoelectric atoms or ions are ions that contain the same number of electrons. So if you have two different things that two ions have the same number of electrons, whichever has the higher number of protons is going to be smaller and hold on to its electrons better. So I think in the summative, the examples that I gave you was Cl minus and Ar. So chlorine normally has 17 electrons. Now it has 18. Argon has 18 electrons. And so now we have this. This is isoelectric. So they have this guy has the same number of electrons as this one, but he has more protons, so he's the one that gets to meet this criteria. Smaller, size, he's smaller overall and has a better hold on his electrons. And that's it for me. So hopefully I talked a little bit faster for you guys. If you have any questions, definitely reach out, and we'll just kind of go with the flow as we need to. Take care. Take care.